Hi everyone, welcome. The problem is to design a compromised account detection system. Here are some good questions to ask in the requirement clarification phase. Detect account compromise in real time, alert users, and flag high-risk accounts. What data is available? Are we predicting immediate compromise, high-risk behavior, or both? How quickly must the system respond? How should sensitive user data be handled? How will success be measured? Reduced fraud, true positive detection, false positive minimization, user satisfaction. Let's frame the compromised account detection system as a machine learning problem. 1. Input. The model receives features from various account-related data streams. These include login events, timestamps, device ID, IP addresses, geolocation, MFA usage, transaction history, and behavioral biometrics such as typing patterns or mouse movements. Historical account activity provides context for normal behavior patterns. Combining these features helps the model detect deviations that may indicate compromise. Second, output. The outputs can be a probability score that an account is compromised, a risk score, or a binary flag requiring user verification. These outputs drive automated actions such as triggering alerts, enforcing multi-factor verification, or temporarily restricting account access. Third, ML task. Type. The core tasks are binary classification, compromised, not compromised, and anomaly detection. Classification is used to predict explicit compromise events, while anomaly detection identifies unusual patterns that may precede compromise. Risk scoring can provide a continuous measure to prioritize investigation or automated response. 4. Model choices. For structured tabular data, tree-based models like XGBoost or LightGBM are highly effective. Random forests provide robustness and interpretability. Neural networks, such as MLPs, can learn complex, nonlinear interactions. LSTMs or transformer-based models can capture sequential dependencies in login or transaction sequences. Autoencoders or other unsupervised models are effective for detecting unusual behavior patterns. 5. ML objectives and loss function. The model is trained to minimize classification error using cross-entropy loss. Since account compromises are rare, datasets are highly imbalanced. Custom cost-sensitive loss functions or sampling techniques can help prioritize detecting true compromises while controlling false positives. 6th, evaluation metrics. Key metrics include precision, recall, F1 score, and ROCAUC. High recall is critical to detect as many compromised accounts as possible, while precision ensures legitimate accounts aren't unnecessarily flagged. Business metrics, such as fraud loss prevention and user trust, complement these technical metrics. Let's discuss data engineering and feature engineering for the compromised account detection system. 1. Data sources. The system integrates data from multiple sources. Login events capture when and how users access accounts, including IP addresses, geolocation, device IDs, and MFA usage. Transaction histories and behavioral biometrics provide additional context. Aggregating these sources ensures that the model has sufficient information to detect anomalies or suspicious activity. 2. Data collection and cleaning. Raw data can be messy and inconsistent. Logs must be aggregated from different systems, timestamps normalized, duplicates removed, and missing values imputed. Outlier removal is important to prevent the model from being biased by extreme events, such as automated testing or internal system accounts. 3. Feature engineering. Behavioral features. Behavioral features summarize account activity. Examples include login frequency over various time windows, failed login attempts, unusual geolocations or IP addresses, session durations, and transaction patterns. These features allow the model to learn what constitutes normal versus suspicious behavior. 4. Feature engineering, temporal and sequence. Features. Many attacks involve sequences of events. capturing temporal patterns such as time since last login time of day of week patterns, or sequences of failed and successful attempts is critical. Transaction sequences can reveal unusual spending behavior indicative of compromise. LS, TM, or sequence-based models use these features effectively. 5. Feature engineering, risk and derived. Features. Derived features help quantify risk. Device or location risk scores, velocity features, e.g., rapid changes in location or device, account age, and MFA bypass events provide strong signals of compromise. These features can also be used for explainability and prioritization of alerts. 6. Data storage and versioning. Centralized storage of both raw event logs and processed features ensures consistent input for training and inference. Versioning allows reproducibility, enabling the system to be retrained reliably, and ensuring that features used in production match those used during model training. Let's walk through the model architecture for detecting compromised accounts. 1. Input layer. The input layer ingests all relevant features engineered in the previous step. This includes login events, IP addresses, geolocation, device identifiers, MFA usage, transaction history, and behavioral metrics such as failed login frequency or session anomalies. Derived features, like risk scores for locations or devices and velocity features, are also included to enhance predictive power. 2. Pre-processing and embedding layer. Before feeding the model, numerical features are normalized to ensure consistent scale, and categorical variables like device type, browser, or geolocation are encoded using one-hot encoding or embeddings. Missing or inconsistent data is imputed to prevent bias and improve model robustness. 3. Core model/encoder. For structured tabular data, tree-based models such as XGBoost or LightGBM perform well due to their ability to capture nonlinear interactions. Multi-layer perceptrons, MLPs, can model complex feature interactions, while sequence models like LSTM or GRU are ideal for temporal patterns, capturing sequences of login events or transactions. Autoencoders or other unsupervised models can detect anomalous patterns indicative of compromise. 4. Task-specific layers. A classification head predicts the probability of an account being compromised. Optionally, risk scoring or anomaly detection heads provide additional outputs for prioritization, enabling automated actions or alert ranking. 5. Output layer. The output layer generates actionable predictions, a probability score for compromise, a risk score, and recommendations for alerts or automated account lockdowns. These outputs feed directly into monitoring dashboards and user notifications. 6. Regularization and optimization. Dropout and early stopping prevent overfitting, while class weighting or resampling addresses imbalanced datasets, where compromised accounts are rare. Cross-entropy or cost-sensitive loss functions are optimized to reduce false negatives, ensuring high recall while maintaining precision. This architecture enables a robust, accurate, and real-time compromised account detection system capable of predicting suspicious activity and protecting users effectively. Let's discuss how we evaluate the compromised account detection system, both offline and online. 1. Offline evaluation. Classification metrics. For offline evaluation, standard classification metrics are applied to historical data where compromised accounts are labeled. Precision measures the proportion of correctly flagged accounts among all predicted compromises, while recall measures the proportion of actual compromised accounts correctly identified. F1 score balances the two. RO, CAUC, and PRAUC provide overall model discrimination performance, which is important when class imbalance is high. 2. Offline evaluation. Imbalanced data. Handling compromised account events are typically rare. Standard accuracy can be misleading, so metrics such as class-weighted accuracy or balanced accuracy are used to evaluate performance fairly across majority and minority classes. Precision recall curves help assess model behavior under different alert thresholds. Third, offline evaluation, business impact metrics. Beyond technical metrics, business-oriented metrics are essential. These include the estimated amount of fraud prevented, the number of false positives affecting legitimate users, and reduction in account takeover losses. These metrics help quantify the practical value of the model to the organization. 4. Online evaluation, A/B testing. Offline evaluation is insufficient for real-world deployment. A/B testing allows us to compare the new model against the existing detection system under live conditions. Metrics like detection rate, alert latency, and system load help assess real-time effectiveness and operational performance. 5. Online evaluation, user-centric metrics. User impact is critical. Metrics such as the rate at which users respond to alerts, successful MFA completion following alerts, account recovery time, and user satisfaction indicate whether the system improves security without negatively impacting user experience. 6th, monitoring and continuous evaluation. Even after deployment, behavior patterns can change. Continuous monitoring tracks drift in login behavior, frequency of anomalous events, and model performance over time. Retraining triggers can be defined based on these indicators to maintain high detection accuracy and low false positives. This evaluation framework ensures the model is accurate, operationally effective, and user-friendly, balancing technical and business requirements. Let's walk through how the compromised account detection model is deployed and served in a production environment. 1. Containerization and packaging. Before deployment, the trained model is packaged along with all dependencies using containerization tools like Docker or MLflow. This ensures consistent behavior across development, staging, and production environments. Versioning ensures that previous model versions can be reproduced or rolled back if needed. Second, serving infrastructure. The model is deployed as a microservice with REST or gRPC endpoints. When a login event occurs, the system sends the event data to the model service, which returns a prediction of account compromise probability or risk score. Microservices enable modular scaling and easy integration with existing authentication and security systems. 3. Scalability and load balancing. Compromised account detection requires real-time processing at scale, often across millions of login events per second. Horizontal scaling allows multiple instances of the model service to run in parallel, while load balancers distribute requests to avoid bottlenecks. Auto-scaling ensures resources adjust dynamically based on traffic. 4. Latency optimization and streaming. Real-time detection is critical. Event streaming pipelines using Kafka, Kinesis, or other message brokers allow login events to be processed as they occur. Asynchronous processing and caching of frequent patterns reduce latency and improve user experience. 5. Monitoring and logging, continuous monitoring tracks, prediction latency, false positive and false negative rates, system health, and potential model drift. Alerts can be triggered if performance metrics degrade, ensuring that compromised accounts are detected accurately without disrupting legitimate users. 6. Continuous deployment and rollback. CI/CD pipelines automate testing, deployment, and versioning. Safe updates allow new model versions to be deployed with minimal downtime. Rollback mechanisms ensure that if performance degrades, the system can revert to a previous stable version quickly. This architecture ensures the compromised account detection system is scalable, reliable, low latency, and maintainable, providing real-time protection to users while minimizing false positives.